Okay, guys, so today's our lecture is about response spectrum analysis, as I discussed in a previous video when we were defining the shear wall, that we will be continuing with that model. You can continue with that model, or you can define a new model. It's up to you. You can apply response spectrum to any structure you want. For instance, let me start with the new structure for the clarity, nothing else. Let me make the units to fit 3D. Let's suppose I am going for a 10. Oh, okay, 10 story will be too complex. Make it 5 story, 4 and 4. Okay, keep it 12 feet, uh, 30, 30. Right. For section properties, add new property, make it concrete. For example, I feel convenient working with the concrete. You can go for the steel as well. Make it 1.5 by 1. Make it beam design. Okay. Concrete properties are 4000 and steel is 60,000. Okay. Give it a name of let's suppose beam. All right. Add copy of the property. Name it column and make it 1.5 by 1.5. Select column, give it number 8. It's up to you, whatever kind of reinforcement you want to play with, you can assign here. Okay, so you have defined beams and columns. Okay, select column for the column and beam for beam. You can edit in the grid right here. For example, make it just like we did minus 40 and 40 if I remember correctly. Okay, this is your grid, right? Now you have defined the beams, you have defined the columns, you are left with the wall, and you are left with the what I will say, um, these slabs. Okay, so select all these supports, assign them fixed. Okay, so you have fixed the supports. Now define area element, area sections. Okay, in shell add new section, make it shell thin, name it as a wall. The thickness is 1 feet. Okay, which is equivalent to 12 inches. Add another section, name it as a floor. This time I'm not distinguishing floor and roof, I'm just making it simple, so make it let's say 9 inches for all of them. So 0.75 feet, right? Now you have defined floor, you have defined wall. Okay, right now I am at this level, at the top level. Okay, so what I will do is I will define the floor. Okay, this is the way to define floor. Okay, now select it, go to edit areas, divide areas, and select this option C, number 3, divide areas based on points on area edges. Okay, and select this third point, selected point objects on area edges. Click OK and see, now these are divided. See, previously it was a single slab. Now what you can do is you can replicate it. Just select, okay, again go to edit and select replicate. Now in replicate, see, you are at this level, so you can replicate it to 1 2 3 and 4, right? Number of increments you can give it 4. And if you remember the height of story, it was 12 feet, right? You wanna replicate it linearly, so you don't want to delete the original object, right? Click OK. So when you go down, For example, you are at 60 feet. Okay, go down at 48 and see the slabs are there, right? Go down at 36, slabs are there. Go down at 24, slab is there. Go down at 12, slab is there. Okay, and at the footing there is nothing. Okay, so you have easily defined the slabs or floors, and you have assigned it with simple commands. Now there is a need to define the walls. Okay, so instead of working in xy plane, now you can change the plane to xz. Okay, see, the blue color shows where you are working. So if I come to this point, so this is the point where I want to assign the shear wall. Okay, so select the wall and just click in the desired location. So you have done it. You are working in y is equal to 60, right? Now come to y is equal to minus 60 and draw walls in it. So you are done with the xz plane. Come in the yz plane. See, you are at x is equal to 60. So you need to define the shear walls here, and then come to x is equal to minus 60. Okay, give it some time. Here you are at minus 60 and draw the shear walls, right? So you are done with these steps. You have defined the all these section properties, the frame sections, the area sections. You have assigned the frame sections and area sections. You can check, see, this is your structure. Right now, what you can do is go to this option, select all, right? We have select everything. Go to assign joint and joint constraint. Okay, and select the diaphragm. Add new constraint, give it name, let's suppose diaphragm. Put it z-axis, assign a different diaphragm constraint to each different selected z level. Okay, and click OK. Click OK. Okay, now what you are left with is defining the response spectrum, right? You have modeled the structure, you have defined the support conditions, you have modeled it. Go to the define menu, select the functions and response spectrum. We already done these things in time history analysis, and you know all these things. Okay, so in choose function you can select the drop down list or whatever comforts you feels okay with. You can select that code. Okay, for example, right now I am selecting UBC 94. You can select UBC 97, or you can even define the user defined your own response spectrum. Okay, you can select user defined, add new function, and then you can put the properties of your response spectrum function. For example, in UBC 94, add new function. See, this is the response spectrum. Just give it a name, let's suppose. Keep in mind what the values I am giving here. For example, the function damping ratio is 0.05. Okay, the seismic zone factor z is equal to 0.4 and soil type selected is 2. Now this is the defined function and this is its plot. For example, when I am at 0, I am talking about x-axis. Okay, Just see, I'm going on x-axis. The red dot will show you what will be the value of y-axis at that point. So when my x is 0, see what is the value of y? It is about zero point 0.4, and you can check it from here. See, when my x value is 0, the acceleration is 0.4 g. When I am moving forward at this point, for x of at x is equal to 0.15. By the way, on x-axis the values of time period, and on y-axis this is the value of acceleration in terms of g. So when I'm moving forward, for example, at this point 0.15 time period, so the acceleration is 1 g. And when I'm going forward, for example, up to this point, it is still 0.59. See, this uh, you can see the values over here at 0.59. The values are still 1 g. This is a very big force acting on the structure. When you are moving forward, it is coming down. For example, you are going to the tall structures of time period 2 second, which is almost equal to 20-story structure. So the demand is now reducing. Okay, the g value is reducing to 0.3 g. And when you are going further, for example, 100-story structure, the demand is reduced to 0.06 times of the g. So this is what response spectrum tells you about. Okay, uh, click on OK. So you have defined one response spectrum function. Click on OK. Now go to define again and select the load cases. In here, add new load case, right? Give it, for example, I want to give it a name of response spectrum 1. And of course, I will select the load case type as response spectrum. Please make sure that the model combination is CQC, which is complete quadratic combination for the model combination, and SRSS, square root sum of squares for directional combinations. Okay, uh, we are done with this part. Now come to the load applied part. Select, make sure that load type is acceleration. Select U1 here and put 32.2. I know you are familiar with what is 32.2 in FPS system. It is a value of G. Add, select U2. Okay, make sure that the function you have just defined as specification 1 in a previous step. Okay, it is selected here, and I want to make it 30% of the G in U2 direction. Okay, add. Make sure that it is 0.05, the model damping which you have selected. Click OK and come to the model and modify it. Okay, in model, select the Ritz vectors and make the maximum number of modes to 20. And in loads applied, select acceleration. In UX, add, make it UY, add, and select the OK. Now your structure is ready to run for the analysis. Just click this button. Make sure all the options or all the cases are in run action. You have selected it to run all the cases, for example, dead load, model, and response spectrum 1. And click run now. It will ask you to save the structure first. So when it comes, I will save it. For example, see, I have worked up to 10 story. I will make it a 5 story. Okay, see, this is what you have obtained. For example, show deform shape for the case of response spectrum. Okay, so this is what you have obtained after running for the response spectrum analysis. If I want to show the animation, click on it. See, this is your response spectrum analysis. By the way, uh, just note it, that the structure is 1, 2, 3, 4, 5. This is a five-story structure, right? And what I have shown you in the functions, if you remember, for example, show the spectrum. The five-story structure's time period will be roughly with 0.5 C. See, this is your time period. And look at the demand on this structure. It is 1 G, which is a very big thing. Okay, 1G is a very big force. The time period of this structure is somewhat close to the maximum demand range or the periods. So this is why you are obtaining the results like that. If I want to check that what is happened in the design, whether my beams columns have passed or not, so check this option, verify all members pause. It says that 55 concrete frames failed the stress capacity check or not designed. Do you want to select them? Yes. So after selecting this option, it will show you which one are. See, for example, the dotted one. You see it, right? The dotted ones have been selected and they failed. I think most of the columns have failed. Okay, especially near to the shear walls, because the shear wall was the most stiff part, and it took the most of the load from the uh, coming demand. By the way, the design has been done on the basis of ACI 31805 and IBC 2003, the loading combinations. Okay, so this was the method of applying the response spectrum analysis. You can work, for example, if I will unlock it. So here you can see the selected the dotted columns that are filled in this analysis. See, so these columns were filled due to response spectrum. Okay, you can go to define, you can go to functions, you can go to response spectrum, you can add new function based on ASHTO. You can work with different kinds, for example, the Eurocode from file. If you put a file in the directory of SAP, you can just directly go and browse it, and it will ask you that where is your file. Okay, if you have put it in it, it will definitely show you that okay, what kind of response spectrum do you have, right? So if you have defined your own response spectrum, just put it in a directory where you have saved the SAP 2000 and just take it from here. You will be running your model for that particular response spectrum. This is IBC 2003, 2006. Whatever thing you want, you can take it here. You can define for UBC 97. See, each code has different requirements. For example, in the UBC 94, you have noticed that there were two things. One was soil type, which you selected 2, and the other was a factor like, for example, if I modify this, see, the other one was seismic zone factor Z. But the requirements for UBC 97 are different. You know what is CA, what is CV. You already learned these coefficients while working on the static lateral force procedure, and I have explained each and everything over there. The response spectrum is a huge thing. The topic requires a lot of knowledge of dynamics and earthquake engineering, and unfortunately I cannot provide you all the knowledge in this single video or in this single course. So you have to go and check the details about what response spectrum is and what it offers, and what are the advantages of using it and what are the disadvantages of using it. So In this video, we are done with what we were supposed to do. See you in next video with other topic. Thank you very much.